So 11.3, we're going to be looking at contingency tables, or this is kind of a chi-squared. They'll call it a two-way test. We are dealing with a two-way table, or a test of independence. Okay, and the idea is here I have a table. I can't run the goodness of fit because I have two categories. And what we want to do is we want to figure out whether these two categories relate to each other. Okay, winning team data was collected from 4 teams in different sports with the results shown below. Do you think there's a relationship between whether the home team wins playing at home or whether the home team loses at home, right? Do you think there's some relationship between that? You're like, well, yeah, you play at home, you got everyone cheering for you, you're more likely to win. Okay. Do you think that that differs depending on what sport you play? Like, do you think basketball or baseball or hockey or football, that one of them might have more of a home field advantage than another group? See, that's kind of the question we're asking. Are these categories independent or do they affect each other? Does the sport and whether or not you win at home or lose at home, does home field advantage differ by sport? Okay? This is called the test of independence. We're going to test the hypothesis there's no association. The type of sport is independent of the home team win or loss. The alternative, HO and HA, is that they are dependent. Okay? I'm going to go ahead and take this list of data, and I've already written it on a separate sheet of paper. I'm going to encourage you to do that as well. Feel free to pause if you need to. But we are going to learn how to calculate the expected, because the chi-squared is still observed minus expected squared divided by expected, and add them up. The difference here, we've got 1, 2, 3, 4, 5, 6, 7, 8 different categories to do that with. Ooh, buddy, right? Okay, let's see. So here's my observed. And to calculate what we expect if they were perfectly independent, we need the totals. So write in each number and fill in the totals. The total basketball was 198, baseball was 100, hockey was 93, football was 99. And the total home wins was 287, total home losses 303, and our total here is still 490. Okay? So what would we expect if things were perfectly independent? Well, this goes back to chapter 4 about probabilities. Okay? So the probability of it being perfectly independent is going to be the probability of A times the probability of B. You can just multiply them if they're independent. So the probability of getting a home win and hockey would be the probability of a home win, 287 out of the 490, times probability of hockey occurring, 93 out of the 490. So that's this 287, that's this 93, and each one over 490. This is what would occur if everything was perfectly independent. Okay? What would we expect? How many would we expect? Well, that would be the probability of it occurring. So to get that expected value, we're going to take the probability and multiply it by n. So what happens? 287 over 490 times 93 over 490 times n, which is also 490. See, one of those 490s is going to cancel out. Okay? So 287 times 93 over 490. We got a calculator. 287 times 93 over 490. And let's go ahead and get a decimal for that. 54.4714. That would be what we would expect. 54.47. Okay. Let's do another one. I just want to get a couple where we do this. Let's go ahead and calculate. Did they do that? I did that in the wrong spot. Sorry. Because that was home win and hockey. So that was this third one over. So that was the 54.47. Okay. Let's go ahead and calculate this right here. What's the probability of home loss and hockey? Well, that would be probability of home losing, 303 out of 490, times the probability of hockey is still 93 out of 490. But if I want my expected, I'm going to multiply that times n, times 490. One of them goes away. So 303 times 93 over 490. 303 times 93 over 490. 57.5. If everything was perfectly independent, I would expect there to be 57.5 right there. One more, but this time I'm going to show you kind of the formula that they'll have in the book. To get the expected, what they do is they say take the total of the row, I'll do this, take the row total, times it by the column total, and divide it by our total. That's our n, okay? Well, isn't that kind of what we did? Why don't we just do row times column divided by total? Well, look, we did the probabilities times n. One of these canceled out, so it ended up just being the row total, the column total, and one n left because one of them canceled out. Row total, column total, one of these canceled out, right? So if I wanted one more here, let's go ahead and go back up and do, maybe I'll do more than one. Let's do this one and this one, okay? So if I want home wins and basketball, home win and basketball, what I'm going to do is take the total of the row, 287, times it by the total of the column, basketball, 198, and divide it by the total, 490. Why does that work again? It's basically the probabilities times n. One of the 490s cancels out. 287, 198, let's see, 287 times 198 over 490. All right, how about 115.97? And 71, we'll do home loss and basketball. This time I'm doing home loss, so the total 303 for the row. Column is still 198 over the total 490. So 300, 198, 300 times 198 over 490, 121.22. Alright, so we've already done like half of these. This wouldn't be horrible. I've had some people that have difficulty running this test or remembering how to follow the instructions, but they've had these kind of row times column divided by total, and they're able to calculate each of these by hand, add them up, get a chi-squared, do chi-squared PDF. You can totally do this test by hand. I don't want to, though. So what I'm going to do is I'm going to go ahead and show you how I would deal with this using some technology. Okay? So here's how we're going to get this chi-squared quickly with technology, and we're also going to get that expected. But I am going to come back because to get full credit, this must be filled in. You have to actually list the expected to get full credit on the chi-squared two-way table test. Okay? So here's what we're going to do. This is kind of the weirdest thing we do, but it's not too bad. We are going to define, okay, and we need to basically we need a matrix, and I believe we'll just call it A. Define A is the matrix, and this matrix of data is 4 rows by 2 columns, okay? So to set up a matrix, I'm going to choose this button right here. That was not what I wanted. This button right here. There we go. And if I look in there, there's a matrix right here. 2 by 2, 1 by 2, 2 by 1. This is like, I need something bigger. We need something bigger. We need something that is 4 by 2. Row by column, 2 by 4. So that button right here again next to the catalog. Select the matrix there and rows 2 by 4. That looks like the size of data we have. And then we basically fill it in. 127, 71, 53, 47, 50, 43, and 57, 42. Once you hit enter, you have done all the hard work that is required for this test. I get that this is weird to do, define and name something A and create a matrix, but that's the hardest thing. So define A equal to, choose a matrix that is 2 by 4, and fill it in and hit enter. That's as hard as this test is going to be to run. Okay. Once you have that set up, once you have this defined, okay, watch how easy it is to run this test. Menu, statistics, tests. We're doing a chi-squared, aren't we? The goodness of fit was where we had to go and like fill in a list and fill in the expected. This one's actually way easier. The two-way test, or test of independence, we do in the calculator page, and we just got to do that define part because here's all it needs. It's like I could run this entire test if you could just tell me where the observed matrix is. Man, if there was only some way that we could have defined that, right? Well, we did. The observed matrix is A. Done. You define the observed matrix, so you call it A, and it'll run the test on that. It gives us the chi-squared, it gives us the p-value, okay? So I'm going to go back here and say, you know, how did it get that chi-squared? It did each observed minus expected squared divided by expected, added them all up, and got us the chi-squared value of 4.737. And a p-value of 0.192, and degrees of freedom of, and how did they get degrees of freedom of 3? Basically, the number of rows minus 1 times the number of columns minus 1. How many rows were there? How many columns were there? So 1 times 3 is 3. The calculator will always do that for you, but that is how they do the degrees of freedom. Rows minus 1 times columns minus 1. Okay? Here's the problem. I told you that I needed an expected matrix. I needed you to fill this in for full credit. They have the expected matrix right here. It's just kind of truncated because it's a big old set of data. So how do I get the expected matrix? You see where it says stat.results? That's where you get the results of all the tests. If I want just the expected matrix, it's a very similar command. It's stat dot. It's like, whoa, what do you want? What do you want? Degrees of freedom? You want the computated matrix? You want the expected, the p-value, the results? What do you want? We want the expected matrix. Double check these numbers. 115.97. What number did we have? 115.97. Whoa, we messed up on that one. What was that one? 303. Alright. See, I'm feeling way off on that one. What is that one? 303, 198, 490. I need to do that real quick. 303. Maybe some of you caught this already, but that still doesn't seem like it's. You must have typed it all crazy. By 490, 22. What did this just say? 82. What am I missing? This adds up to 203. So both of those are going to be off. So that's not 300 or not 2, it's 203. Okay. So that's why I double check our numbers. So let me go back to that. So I want 82 because I want to know that I'm not totally crazy. If I change that to a 203, how about 82.0286? that what that got? 82? Feeling better? 58? 41? 54 looks good. This one's off. Ruh-roh, right? Well, I remember I did the freaking 303 instead of 203. So let's do 203 and 490. 203 and 93. 203, 93 over 490. How about 38.52? And what does it have? 38.52. What is this? 57.98? Or I guess 99. And this one is 41.01. Okay? So you need to fill that in. Make sure you fill in the observed and the expected, the chi-squared, the p-value. We ran the test. Write a conclusion. How do we write our conclusion? Well, this p-value is greater, so since, I ran out of room, since the p-value is greater than alpha, we fail to reject what? What was our null hypothesis? The two categories, the sport and the home advantage, right? The sport and home field advantage fail to reject that they are independent. Okay? So that's it. That's how you run this test. It's not super hard, but we are going to practice, looks like 1, 2, 3 more, just to kind of get some practice of this. Okay? So let's go ahead and go through 3 more, and we got this. So I'm still going to go through the whole PRTC. So what are we dealing with here? Not really proportions. We're dealing with two categories. The contingency table below shows how a random sample of college freshmen graded the leaders of 3 different types of institutions. Test that claim the grades and types of institution are independent. So our population is going to be the grading versus type of institution. What are the requirements? This data had to be collected randomly. Done. What else? And they didn't list these on the last one. I'm going to go ahead and list them out. We need there to be, basically it needs to be 2 categories. We have grading as one category, institution is another. Okay. What else do we need? They'll say at least 5 in each category. Now this is going to be a problem because I already see some that don't have at least 5, right? I think just that one. I've seen in some books where they say at least 5, but generally what we do is we say at least 5 in approximately 80% of the categories. And why 80%? It's kind of the idea of like if some of these are greater than 5 and some of these are less than 5, as long as 80% of them are greater than 5, they'll average out to being about 5 in each. Okay, so we need at least 5 in each category, not in every single one, at least 80% of them. There's only one missing, we're going to be fine. Okay, what test are we going to run? Chi-squared. Not goodness of fit, not putting this as a row of data and then putting in the observed and the expected. That's different. This is called a two-way test or a test of independence. What's our null hypothesis? Grades and institution. Type are independent. Alternatively, the grades and institution type are dependent. I'm about ready to run this test, but do keep in mind if you want full credit on this for the test or on the quiz, you will need to fill in an expected matrix. This is 3, 4, 5 by 3, so 1, 2, 3, 4, 5 by 3. So you'll need to fill in that expected matrix, okay? Now I'm going to let the calculator do some heavy lifting, so let's go ahead and do the most complicated part about this test. Define. And that command is in there somewhere in the rules. I just know how to type it in. So define A is equal to, so we're going to redefine A as a matrix. That's this button. Select the big old 3 by 3, and what did we say here? It has 3 rows by 5 columns. Okay, and let's start filling in these numbers. 25, 46, 19. Five, 3. This was a 7 and a 5. 18, 44, 24. And 5, 23, 37. 21 and 12. That is the most complicated part about running this test. And it's now done. It even said, done. Makes you feel good, right? Once you have that, menu, statistics, tests, chi-squared, not goodness of fit, not one category we have, right? We have multiple categories that we're comparing. It's a two-way table, two-way test. Our observed is in. Done. What do I write down? Our chi-squared, 48.48. Our p-value is basically 0. Don't put this, basically this has like 7 zeros in front of it. So if you want to put like 7 zeros and then try to fill that 7 or 8 in, you can. I'm just going to call it 0. I don't remember if they gave us an alpha. So I'm going to call alpha 0.05. Degrees of freedom should be 4. 8, I can't multiply because it's 3 minus 1 is 2 times 4, so it's 8. Okay. Based on this, we're ready to write a conclusion. Let's make sure we fill in this expected. They put it right here for us. That is not helpful. How do I get to it? Stat.results. So stat, down here, stat dot, what do we want? The expected matrix. I don't need all the perfect numbers, but just, 37.7. These are all, what, 16s? 37.7. 37.7. 26.7. 26.7. 26.7. 11, 11, 11. 6.7. Okay, those are our expected. How do they get that chi-squared value? Every observed minus expected squared divided by expected. All that freaking 3, 6, 9, 12, 15 times and then added. Thank goodness for technology, right? The last thing you need is to write a conclusion. That p-value is ridiculously low, so we say since the p-value is less than alpha, we what this time? We reject that the grades and institution type and, oh gosh, I can do better than this, come on, and institution type. Reject that they are independent because they didn't meet what we expected if they were independent, and conclude they are dependent. Whew. Okay, so reject the null hypothesis, conclude the alternative. One more. I say that. Two more. Big liar. Okay. Let's see. What I'm going to do on these is I'm going to go ahead and we're going to run the test just to practice it and write the conclusion. So the PRTC, that's fine. We've done that to death. Let's go ahead and run the test. So we've got a 2x2. I'm going to define matrix A as a 2x2. So I can choose this and tell it to do 2x2 and 276, 1376, 338, and 3485. Done. Let's run this test. Statistics, tests, chi-squared, two-way. Observed was in A. What do we need to write here? We need our hypotheses. Obviously, they're still going to have P, R, so check those out. T, we are running A, chi-squared, two-way test. What do we have? We have hypotheses, our two categories. Queen Elizabeth and Royal Caribbean both experienced outbreaks of norovirus within 2 months of each other. Results are shown in the table below. Use a 0.05 significance test that getting the norovirus is independent of the ship. Okay, so it's going to be the ship type and norovirus outbreak. Are independent, and the ship type and norovirus outbreak are dependent. Okay? Once we have that, we have an alpha 0.05. We have a chi-squared of 71.68. We have a p-value of dang near 0. We have degrees of freedom, should be 1 this time. 2 minus 1, 2 minus 1, multiply those. Alright. And I'm ready to write the conclusion. We still need to fill in the expected matrix. 2x2. What are our expected numbers? You can do row times column divided by, row times column divided by n. Totally do that. Or, since you've already run the test, stat dot expected matrix. 185.3 428.7 1466.7 and 3394.3. Okay. So those are expected. We got all this. What is our conclusion? Since p-value is less than alpha, we reject. The null hypothesis that the ship type and norovirus outbreak are independent, and conclude they are dependent. What does this really mean? Well, if I was going to go on one of these ships, it's more likely or less likely for me to get a virus, basically. Okay? even though they had the same time, they had a much larger outbreak in the Queen Elizabeth, you were more likely to get that virus being on the Queen Elizabeth than if you went on Freedom of the Seas. Okay, so there is a relationship here. And last but not least, recent years concerns have been expressed about adverse health effects from amalgam. There we go. Amalgam, that's not that bad. Amalgam dental restorations, which include mercury. Table below shows results from a study in which some patients were treated with amalgam restorations and others were treated with composite restorations that do not contain mercury. Use a 0.05 significance level to test for independence between the type of restoration and sensory disorders. So basically, the mercury can cause disorders. So is there a dependence? Did one affect the other? If you got the transplant with the restoration with mercury in it, did that basically cause you to potentially get your senses affected? Okay. PRTC. What we are dealing with sensory disorder and dental restoration type, right? The requirements: data must be collected randomly, at least 5 in each. 2 categories. Third, let's run the test. Chi-squared, 2-way table, 2-way test. Our null hypothesis. Category 1, sensory disorder. And category 2, dental restoration type. Are independent. Alternatively, the sensory disorder, category 1, and the dental restoration, category 2, are dependent. How do I run this? You got a calculator, I hope. The complicated thing to do for this test is to define. A is equal to, this time it's a 2x2. I'm getting all excited here, ready to run the test. Set it up. Oops. Oh, undo. Set it up as a 2x2. Let's fill in our numbers. 36, 28, 231, and 239. Done. Now we can run the test. Menu, statistics. We are doing a test, chi-squared 2A. We observed it and put it in A. Write down the chi-squared, 1.136. P-value, 0.286. Degrees of freedom should be 1. And let's write down our expected matrix. Stat.expected. 32, 32. 235, 235. This is what we would expect if there was no relationship. Were the numbers far enough off to make a significant difference? Well, p-value is greater than our alpha, which means we conclude that what? Since the p-value is greater than alpha, we fail to reject that what? The sensory disorder and dental restoration are independent. What does independent mean? They didn't affect each other. People got the sensory disorders or didn't get the sensory disorders, and there really wasn't a significant difference between them. Okay? So that's good. So we don't get to sue anybody this time, unfortunately, but that's it. So that's our last test for this week. Have a good time, and I will see you all soon.